Okay, so with this Markov chains, the first thing to do is set up what is called the transition matrix. You have to, it's always going to be a square matrix, and you want to make sure it goes in the same order in both directions. So here we go. So Anastelle is doing a test, or she's taking tests, right? Or I'm sorry. So every day she can have a lesson, practice, quiz, or test. So that's her 4 states she can be in. So it's either going to be a lesson, a practice, a quiz, or a test. So you want the top of the matrix lesson to go in that exact same order. And then each one of these rows is going to be the probability. If she starts here, the next day, what's the probability it's going to be any one of those? And each one of those has to add up to 100%. And it's going to be decimal form. So it says, following a lesson, so here she's at lesson, that's where she's starting. The next day, 55% chance she's going to practice. So make sure you put that practice. There is a 25% chance she's going to have another lesson. There's a 15% chance she has a quiz, and just a 5% chance that that'd be 05. And if you added those up, they'd add up to 100 or 1. The following a practice, the next day, quiz is 40. 30% chance she has a test. 20% chance she has another lesson. And just a 10% chance she has more practice. And again, those would add up to 101. Following a quiz, the next day, there's a 70% chance she has a lesson, 20% chance she has lesson test, 20% chance, and there's a 10% chance of that's 100%. So there's no chance she's going to have a quiz following a quiz. And then following the test, the next day, 80% chance she has a lesson, and 20% chance that they have practice. That's the 100%. So there's no quiz following a test. There's no test following a test. So that's your transition matrix. And we'll call that the T matrix or whatever you want to put it. I guess if you're going to put that in the calculator first, let's just call that the A matrix. So when you start looking at the questions, her initial state matrix, which is where she begins, is based on this. So if Anastelle's lesson, if she has a lesson on Monday, so you're going to do her initial state is going to be always a 1/4 with, and it's going to be the same order: lesson, practice, quiz, test. So if she has a lesson, that puts her one person there. What's the probability she'll have a test on Friday, which is 4 days later, 4 transitions? So that'd be times that transition matrix to the 4th power. And then you're going to get 4 decimals. And what's the probability she will have a test? It'll be the last number, because that's where the test falls. So if she has a quiz today, that would make her 0010, because the quiz is the 3rd, times what's the probability she'll have a quiz in 7 class days. So you'll multiply times the transition to the 7th power, and then you're going to get 4 probabilities. Those 4 probabilities will still add up to 100%, and just choose the quiz one. So I'm not going to put all of these into the matrix calculator because I think you guys can do that. If Anastelle has a test today, so test today would be 0001 times, what's probably she has a quiz or test in 10, so it'd be to the 10th power. And then quiz or test, you would take the quiz and the test probabilities and add those two together. So whatever those two are, you just take the sum of them. So if the teacher observed on a random day, what's the probability she is teaching a lesson? So what you're talking about here, and this is kind of the same as number 6, is that as you go out to great numbers, so we don't know where it started at, and you could put just one anywhere. You could actually do 0.25, 0.25 for each one of them, just to spread it out if you wanted to. It does not matter, not equals, times that transition matrix, and take it to just a big power. 50 would probably work. And when you take it to a large power, it turns into what's called the stable state vector. It gets constant. If you checked it and took it to the 51st power or even the 60th power, if you did it a couple times, those numbers aren't going to change. And of course, the lesson was the first one. So just when you go to a big number, it becomes what's a stable vector, which is all those. Questions on that? Okay. So the big thing is setting up the transition matrix. So the next one, so in this one, he can move from, I'm actually going to move this over so I can have some space. Okay. So he can go, or whatever, it's an ant or something like that. Each turn, a contestant can go from A to B, C, D, or E. A, B, C, D, E. So when you have something like motion or something like that, then use fractions. So the transition matrix says if you start at A, if you're at A, it says the diagram shows contestant. On each turn, the contestant must move along one of the lines in the direction of the arrow. So if you're at A, then you can go to B because this is a two-way. You can go to C, you can go to E, or you can go to D. You can go to any one of the four of them. You just can't stay at A. So you'd say you can't stay at A, and there is, since there's four of them, there's a fourth of a chance that you would go to any one of those. If you're at B, you could go to A, or you could go to C. And that's 2. So if you're at B, there's a half a chance that you go to A, there's a half a chance you go to C, and the rest would be no chance at all. If you're at C, you can't go to B, that's not two-way. You can do A, E, that's it, A or E, because D is not a two-way. So if you're at C, you could go to A, so that'd be a half, or E would be a half. So if you have 2 possibilities, it'd be halves. If you have 3 possibilities, just do thirds for each one of them, so forth. So D can go to A, can go to E, can go to C. 3 possibilities, so yes to A, yes to E. Oh, those should be zeros. And yes to C. And again, if you add up going across, it's always got to add up to 1 in these transition matrices. So finally, E, no, no. E can only go to D. So if you're at E, you only have one option. So it'd just be 1. You have to go to D. The rest of them you cannot. So that's the transition matrix. So then your initial state matrix is going to be a 1 by 5 wherever you start out or wherever the contestant starts out. If a person begins at spot A, so your initial state would be 1 and you're nowhere else. What is the probability? So call that transition matrix after 5 turns. So just to the 5th power. And then it's asking for the probability of spot C. Just make sure you're looking at the middle number where C is. If a person begins at D, 1, 2, 3, D, right? What's the probability that they will be at E after 8? So raise it to the 8th power. And spot B is the second one, right? A, B, C, D, E. If a person begins at E, E is the last one. After 10 turns, what's the probability they're going to be at spot E again? So again, the last one. If there is a grand prize for a game, and it should be placed at the least likely spot someone would land on, where should it be placed? So again, doesn't matter where you start someone. You could put the 1 anywhere you want as long as you just do a 1. Or you could even do 1/5, 1/5, 1/5, 1/5, and each one of those just to spread it out, as long as it adds up to 1. Take that to a large power like 50 or 60. That will give you the stable state, and then just pick the one that is the smallest probability there, right? The least likely spot. So hopefully, I mean, after seeing a couple of these, you're getting the idea. Any questions so far? All right. So this one just has 3 states. A man can be a professional, he can be a skilled laborer or an unskilled laborer. PSU. Penn State University for those that. Okay. Assume that a son of a professional man. So if it's a professional man, so this is not what the person is doing. This is what dad is, and then what son is going to be. So if the man's a professional man, then 80% of his children will be professionals. Excuse me. 10% skilled labor, and that's 90. So it's got to be 10%. And it says that. If it's a skilled laborer, 60% of his children will be skilled laborers. 20% professionals, that's 80, so it's got to be 20%. That's what it says. Finally, 50% of the unskilled will be unskilled. 25% in the other 2 categories, which make 100. I'm going to call. So there's your transition matrix. Each one adds up to 100. Allergies are kicking in this morning. Okay, so assume that every man has at least one son. Form a Markov chain following the profession of random chosen son given through several. Set up. Okay, that's the transit. That's what we just did, number 11. What's the probability that a grandson of a professional is unskilled? So in that case, it's starting the grandson of a professional. So you start with a professional times your transition matrix, and son would be 1 transition, grandson is 2 transitions. And then what's the probability he is unskilled? That's going to be the 3rd one. Find the probability of a random chosen great grandson of an unskilled. So unskilled would be there. Great grandson would be 3 transitions: son, grandson, great grandson. And then what's the probability that he is a professional would be the first one. And the stable state, raise it to the, I always do 50th power, but whatever. And that'll give you the probability of each category after a long period of time. All right, mazes are, so this maze has no exit. There are 6 rooms of this gallery. If someone in a room, they have an equal chance of being in the same room or an adjacent room after a 10-minute period. I'm actually going to shrink this down a little bit to give you room. So they can stay in the room they're at. So this would be a 6 by 6. A, B, C, D, E, F. A, B, C, D, E, F. So if you're in room A, you can leave. There are 2 doors, or you can stay in the room. So there's 3 possibilities for room A, because it says they can stay in the same room. So A would be a third of them stay in A third go to a B, and a third can go to D. Can't get to the other rooms. If you're in room B, you have 1, 2, 3, 4, or stay, so there's a 5th. So a 5th can go to A, a 5th can stay in B, a 5th can get to C, a 5th can go to D, and a 5th can go to E. The only room they can't go to is F. Can't go to F from there. If you're in C, you have 1, 2, 3, or stay, 4 possibilities. Can't get to A. You go to B from, you can stay in C. Can't get to D, you could go to E, or you could go to F. D has 3 doors plus stay, so that's 4 ways. A, B, can't get to C from D, you could stay in D. You go to E, can't get to F. E has 3 doors or stay, no A, you go to B. And you could do 0.25s for these if you'd rather, but fractions are, like you can't do decimals for these because it's a repeating decimal. From E, you can get to C. From E, you can get to D, or you can stay in E, can't get to F. F has 1 door or stay, so there's 2 possibilities. And that is go to C or stay in F. So that would be your transition matrix. If there is a place they can't leave from, that's called an absorbing state. That would be like if I said you couldn't leave the room once you're there, then eventually everybody would be in room F. And your stable state would show that. If someone in room A, what is the probability that they will be in room E after 60 minutes? So I did go back and read something. I didn't pay attention to how often the transitions are. So the every 10-minute period. So 60 minutes won't be 60 transitions, it's just 6. So if somebody's in room A, 1. So that'd be a 1 by 6 times your transition matrix to the 6th power for 60 transitions. And then pick room E, right? There's A, B, C, D, E, F, and pick the probability for room E. If someone's in room D, A, B, C, D, E, F, what's the probability they'll be in 9 transitions, 90 minutes? A, B, C, D, E. what's the probability they're there in F? If someone starts in room B, what's the probability after 120 minutes they would be in room A or B? You take those two and add them together for or. Oh, C, D, E, F. Those don't matter. So A or B, you would add them. And then again, what's a stable state? Doesn't matter where you start somebody. When you do it to a big power, you're going to see what rooms they're most likely going to be in after a long period of time. So yeah, setting up that transition matrix is probably the biggest part of these problems, and pay attention to make sure that it gives you time, figure out how often it goes on. All right, so last one, you got victims of disease will be treated annually. They can be cured, temporary remission, sick, or dead. So they can be cured, temporary remission, sick, or dead. Cure, temporary, sick, dead. Okay, once a victim is cured, he is permanently immune. Each year, those in remission get sick. So once a person is cured, they're going to stay cured. They don't go into those. They're permanently immune. Each year, those in remission get sick again with a probability of 1/4. So those in remission get sick again, 1/4, are cured half the time, or stay in remission 1/4 of the time. Those who are sick are cured, go into remission, or die from the disease. Those who are sick either are cured, go into remission, or die from the disease 1/3 of the time. And of course, those who die cannot leave. So this actually has, anytime you have a 1 on that diagonal, there are 2 absorbing states. If you get cured, you stay there. But if you die, you stay there. So there's 2 absorbing states. So if somebody's in remission, what is the probability that they will still be alive after 5 years? So somebody in remission is the second one. You would do 5 transmissions. And alive, if you think about it, cured, remission, sick, or dead, alive would be all of those added together, because all 3 of those are alive states. If someone is sick, what's the probability they'll be cured within 8 years? So if they are sick, what is the probability they are here, cured, 8 years? And in the long run, what percent of the sick patients are cured and what percent will die? So in this case, it does say what percent of the sick patients. So let's start somebody that's sick. But in the long run, it really doesn't matter, other than if you started like we usually do, somebody here, they would never leave being cured. Or if you put your 1 here, they would never leave. So it has to start at one of these 2 that are not absorbing. Raise that to the 50th power, and you'll see what percent in the long run are cured. And really, when you raise it to a stable state, these 2 should be zeros, because either after 50 years, they're going to be in one of those 2 categories, based on the assumption they're not just going to die of old age. I think that's the last one. Yeah. No, there's one more in there. 10 of 12. Is there one more? Gonna get cold this weekend. Okay, food services, local high school, determine whether students eat in the cafeteria in the future. The following result. So if a student eats in the cafeteria, I think this is just a 2x2. Yeah. So that's going to be cafeteria or not cafeteria. Cafeteria, not cafeteria. If a student eats in the cafeteria, the probability he will eat there again is 70%. So 30% would not. And if it didn't give you both of those percentages, well, that has to be 30, right? If a student eats in the cafeteria on a given day, the probability he or she will, does not, 40%, and the probability he will not eat there is 60. So that's 40, 60. That's a 2x2 transition matrix. Probably should have started with that problem. I'll have to fix that. So suppose that 75% of the students eat in the cafeteria. So this initial one is going to be 75 and 25 because 75 will eat in the cafeteria, so 25 must not, times your transmission. Monday, what percent will eat in the cafeteria on Friday? Remember, from Monday to Friday is 1, 2, 3, 4 transitions. And then what percent will eat in the cafeteria will be the first number again. Find the distribution of students eating and not eating in the cafeteria after 10 days. So if we start out, doesn't really say to start out with that, but it's assuming after 10 days, what's going to happen, right? What about after 3 weeks? So 0.75, 0.25, 15 days, what's going on? And then what's the stable state? 0.75, 0.25 times, that should be t to the 15th, right? T to the 50th, so just raise it. And so in the long run, what percent of the students will eat in the cafeteria and what percent will not? That's the last one. So I am going to